Hello, everyone. Let's begin with a little background. Before, humans began understanding about the universe when they began to question processes that may occur through their observations of reality. Ideas of the prominent people were considered as philosophy until came Galileo Galilei and Isaac Newton, who gave birth to classical physics. And classical physics established the notion that everything operates at certain principles, and that these principles can be known, understood, and explained using mathematics. This results to the post that the movements of the Earth's objects are not random. Rather, they are predictable, as all macroscopic objects exhibit motion that obeys mathematical principles. Hence, the claim that the universe is math. However, classical physics weren't able to explain when objects are very small or moving very fast near the speed of light. This limitation gave birth to the modern physics, where useful discoveries like theory of relativity and electromagnetism upholds. Yet, although many problems were solved by classical and modern physics, attempts to explain the behavior of matter on atomic level using the said branches of physics were consistently unsuccessful. This led to the discovery of a modern version of mechanics called the quantum mechanics or quantum physics that were able to explain the behavior of atoms, molecules, and nuclei. The earliest idea of quantum mechanics was introduced by Max Planck, and that is the focus of this video. Now, we will discuss about the concept that becomes the beginning of quantum mechanics, which is the Blackbody radiation and Planck's hypothesis. So, an object at any temperature emits electromagnetic radiation, called thermal radiation. A careful study of thermal radiation shows that it consists of a continuous distribution of wavelength from the infrared, visible, and ultraviolet portions of the spectrum. So as you can see in the illustration about the illustration of the electromagnetic spectrum, in increasing energy is shorter wavelength, and in longer wavelength is decreasing energy. So on the left is an example of um, illustrations exhibiting thermal radiation. So accordingly, the spectrum of the radiation depends on the temperature and properties of the object. At low temperatures, the wavelengths of the thermal radiation are mainly in the infrared region and hence not observable by the eye. At the temperature of an object increases, the object eventually begins to glow red. At sufficiently high temperatures, it appears to be white, as in the glow of a hot tungsten filament of a light bulb. So, this is what I mean. So you can see, as the temperature increases, the color of the black body radiator changes. So, from a classical viewpoint, thermal radiation originates from accelerated charged particles near the surface of an object. Such charges emit radiation. The thermally agitated charges can have a distribution of frequencies which account for the continuous spectrum of radiation emitted by the object. James Clerk Maxwell's theory of electromagnetism predicts that the electromagnetic waves are emitted as a result of oscillations of the electric charges found inside atoms and molecules within objects. So oscillations are shown in the GIF that is portrayed on the screen. However, by the end of the 19th century, it had become apparent that the classical theory of thermal radiation was inadequate. The basic problem was in understanding the observed distribution of energy as a function of wavelength in the radiation emitted by a black body. So, what is a black body? This illustration is an example of a black body. A black body is an ideal system that absorbs all radiation incident on it. A good approximation of a black body is a small hole leading to the inside of a hollow object. So experimental data for the distribution of energy in the black body radiation at 3 temperature are shown in the next slide. So, a black body also emits electromagnetic radiation of all wavelengths. For example, the sun. The sun is also an example of a black body. Also, a hot piece metal poses as a black body, which is what is currently used to study about black body, with the notion that the distribution depends not on the material, but only on temperature, with a particular wavelength that is emitted with maximum intensity shifting left as temperature increases. So let's take a look at the wavelength distribution of the sun. As you can see, this maximum will move into the visible spectrum at around 4000 Kelvin and above, as shown in the figure 27.2. The radiated energy varies with wavelength and temperature. As the temperature of the black body increases, the total amount of energy, or the area under the curve it emits, increases. Also, with increasing temperature, the peak of the distribution shifts to shorter wavelengths. This is why very hot objects appear to glow like a hot oven, or what we've said earlier, a light bulb filament. As you can see from the wavelength distribution of the sun, as the temperature increases, it shifts more on the shorter wavelength, and it varies directly on the visible spectrum of the visible spectrum. So with the help of sunlight, we can see things. So unlike cool objects, for examples, us humans, womb exists at around 310 Kelvin, we possesses no visible light. That's why we can't see each other in the dark. So this shift obeys the relationship called Wayne's displacement law that says that when temperature of a black body radiator increases, the overall radiated energy increases, and the peak of the radiation curve moves to shorter wavelength. You can see here in our illustration with the wavelength distribution of the sun and the figure 27.2. And this this relationship is where classical electromagnetism could not account. When the maximum is evaluated from the Planck radiation formula, the product of the peak wavelength and the temperature is found to be constant. So this is the equation for the Wayne displacement law, where lambda max is the wavelength at which the curve peaks, and T is the absolute temperature of a body emitting radiation. So Maxwell's theory and equations for electromagnetism was only able to explain where the electromagnetic waves originates, but it didn't entirely fit with the experimental results that were obtained, shown in figure 27.3. And it also didn't explain the observed spectrum of colors or lights that were produced as a result of the radiation emissions. Earlier, if you could recall, the picture about the glowing color of the material when the temperature increases. So, mathematical models that attempts to produce these distributions were able to fit the data for the longer wavelengths, but did not predict that the intensity would dip down on the left for the UV portion. So, as you can see, figure 27.3 shows an experimental plot of the black body radiation spectrum, which is the blue curve, together with the theoretical picture of what this curve should look like based on classical theories. Okay, instead, mathematical models predicted that the intensity would continue to increase as the wavelength decreases and become infinitely large as the wavelength approaches zero. So we all know that this is not probable because if this is right, every time you open the oven, you will be blasted by an infrared radiation. This suggests that the electromagnetic theory still has limitations as to explaining light and energy. So this on science area, this is known as the ultraviolet catastrophe. So, who was able to solve this matter? The one that was able to solve this matter is the German physicist named Max Planck. So Max Planck introduced the concept of quantum of action, or the Planck's constant H, in an attempt to explain the spectral distribution of blackbody radiation, which formed the foundations of quantum theory. In 1918, he was awarded the Nobel Prize in Physics for this discovery of the quantized nature of energy. So in 1900, or most says 1901, Planck developed a formula for black body radiation that was in complete agreement with experiments at all wavelengths, leading to a curve shown by the blue line in the figure 27.3. So, Planck hypothesized that black body radiation was produced by submicroscopic charge oscillators, which he called resonators. He assumed the walls of a glowing cavity were composed of billions of these resonators, although their exact nature was unknown. So the resonators were allowed to have only certain degrees energy En, given by this equation. En, or energy, is equal to NHF, where n is a positive integer called a quantum number. F is the frequency of vibration of a resonator, and H is a constant known as Planck's constant, which has a value of 6.626 times 10 to the power of negative 34 joules second. So Planck proposed that the vibrational energies and the energies of electromagnetic waves emitted by atoms are quantized. They can possess any value, rather, they have certain values from a set of accepted values. So, the n value is what results in quantization, as it can only be an integer, not a fraction or a decimal. Although this hypothesis of Planck was proposed for practicality, it allowed for accurate prediction of the true distribution of black body radiation at all wavelengths. So, as classical physics suggests that energy is continuous to macroscopic beings such as humans, we now know that in the fundamental level it is indeed quantized. As a final note, the key point in Planck's theory is the assumption of quantized energy states. After Planck, his discovery still resulted to more problems and questions. Hence, finding solutions for these problems began the quantum revolution, where more prominent people has discovered more beneficial ideas. This radical departure from classical physics is the quantum leap that lead to a totally new understanding of nature. Thank you.